Hello my dear design engineers. My name is Kevin Kutto, and today in this video I'm going to explain everything about factor of safety, which is popularly known as FOS or safety factor SF. Factor of safety could make a difference between life and death of a end user of your design. It could make a difference between functional and non-functional part, or the difference between profitable and non-profitable design. Now I'm sure that most of you have already know the famous formula for factor of safety. You've already studied it in your engineering. So the question is, why am I making this video in first place? I realized after interviewing thousands of design engineers in my career, freshers, experienced, the people who are 10 plus years of experience into design engineering, that most of the design engineers know the formula, they have by hearted the formula, but they don't understand the concept of factor of safety in details. They struggle to understand how this formula comes into picture, what is the significance of this concept, and how to choose factor of safety in a particular application. Another reason is that whenever I conduct design sessions for aspiring design engineers, factor of safety is one of the most frequently asked questions to me. And that's why I decided to make this video on this topic, so that you all, once and for all, understand everything about factor of safety and enhance your knowledge about this concept beyond just by hearting the formula. So are you ready? Let's begin. And yes, if you're not done yet, please consider subscribing to my YouTube channel. Also press the bell icon besides the subscribe button. It will give you a notification the moment I upload my new video. Your subscriptions, your likes, shares and comments help me to reach out to the larger audience on YouTube, so that I could add value to their career as well. So let's begin with our topic. Now, factor of safety, even though it is a technical concept, even we use this concept in our day-to-day life, and that's what I'm going to explain today. Because once you understand this as a concept, then you'll never forget it. So in our example, we have a Dev. His name is Dev. Okay, so he's going to relocate to Pune in order to study his engineering. So he's in first year of engineering. He has got the admission. He's relocating to Pune. And our question is, how much maximum cash Dev should carry to sustain for a month? This is the question we are answering. Now, I will put a constraint to this question. Dev comes from a very humble financial background. So his father doesn't have a lot of money. So whenever he has to give some money, he has to compromise on a lot of other stuff. So that is the constraint we have to keep in mind. So we cannot use any amount of money you want, but we have to optimize that money. That's the problem we have to solve. So how to approach this problem? The first thing they will start is by calculating basic amount. He will use the calculation, he will use the factors in order to calculate working cash. How you will calculate working cash? You may think of rent, food, breakfast, traveling, entertainment, stationery, medical, tuition, and a lot of other factors. And if you will add what are the cost of these factors, and he will come up with the figure. So he got a 9,000 figure just for the sake of calculation. Okay, and when he was doing these calculations, he made a lot of assumptions. For example, when he calculated the mess charges, he assumed that mess will run for all 30 days. So he made the assumption for that, right? Now, what happens if mess wala goes for chutti? He goes for chutti for 2-3 days. What will happen? Certainly his assumption will not work good, or he will end up spending more money outside to eat outside food, right? So that's very obvious. But when he is doing calculation, he has to make assumptions. Now, if I ask you whether he will carry the same amount of money which he got from the calculation, any person with common sense can tell no, right? He will definitely carry some buffer. So Dev is carrying buffer of 1,800, and that's how, by adding his working cash which he got from calculation and with certain assumptions, adding into that a buffer, he will get the maximum cash, right? Maximum cash is the amount which he is going to carry with him, and which includes working cash plus buffer amount. Now if I have to represent it in a graphical way, we can always say that maximum cash will be always more than working cash with the addition of buffer. The more the buffer, or the more the difference between working cash and maximum cash, he will be on safer side. He will not run out of the money. But again, as we know, his father doesn't have a lot of money, so we have to optimize the buffer, right? We cannot use more buffer, or we have to use reasonable buffer. That's what I am trying to say. Now, buffer is the measure of your factor of safety. So let's understand what is the formula for factor of safety. Factor of safety is nothing but the maximum cash divided by working cash. So working cash he got here by calculation, maximum cash he got by adding these two, right? So in our case, factor of safety is 1.2. Maximum cash is working cash plus buffer. So from this formula, what we understand? We understand that more the buffer, more the factor of safety. More the factor of safety, the safer they will be. He will not run out of the money. But it comes with the cost. It comes with a lot of sacrifices of his parents, and that's why we always want to optimize this buffer amount, right? That's the whole purpose of design engineers, whole exercise of using factor of safety, right? Now the next question is, how much buffer is good in a buffer? What are the factors which you need to consider, right? We are trying to find these answers into next slides, okay? Now this is non-technical example. If you understand this, you'll understand factor of safety very easily. You'll never forget factor of safety in your life, okay? In a technical example like here, we also have to calculate working stress. Working stress is nothing but it is the amount of stress part will be subjected to in a working condition, and maximum stress, right? So maximum stress is the amount which part can sustain to it. This is a threshold amount. Like we had threshold here, maximum stress will be like threshold amount of stress the part can sustain to. So we need to find these two things in our design. So where to find this, how to calculate this, and where to look for this information, we are going to study in next slide. So let's go to the next slide and understand how to get working stress, okay? So definitely, like here we will have a formula for that. This is very famous example used to calculate stress, right? So we have a rod with diameter D, it has length L0. When we applied maximum load of F, it will be extended to L1, and that's how we get delta L as our change in length, right? So what is the stress or working stress we'll have in this rod? So stress is equal to resistance upon cross-sectional area. We cannot calculate resistance directly, but we can assume that resistance is equal to applied load, and that's why it is applied load F divided by cross-sectional area A. If you look at this formula, you will understand that as soon as you increase cross-sectional area, your stress will go down. That means in order to reduce your stress, you have to play with the dimension. So that's how you play with the working stress. Now you know the unit of force N, unit of cross-sectional area is mm square. That's how you get Newton per mm square as the unit of working stress or stress, right? The other factor which we use in stress strain curve, the reason why we are going to look at the stress strain curve is to understand the maximum stress. Working stress we already got here, right? So now we have to look for maximum stress, and in order to get maximum stress, we have to look at the stress strain curve. And in order to look at the stress strain curve, there is another concept which is very important to understand, is a strain. Because stress we already understand, so we have to understand strain as well. So what is strain? Change in length upon original length, or change in dimension upon original dimension is the strain, right? So in this case, it is like delta L by L0. And we know that this is a factor, so definitely it doesn't have any unit. So now that we understand what is working stress, we also understand what is strain. Now that we understand how to look for working stress, so working stress we have to calculate with certain assumptions, right? And how to calculate maximum stress, we have to look for it into the stress strain diagram. So I am going to go a little bit in details of stress strain diagram, and the reason why I want to go in details because you will also understand what is stress strain diagram for ductile and brittle material looks like. So we are trying to hit two birds with one arrow, right? So in the single video you will get that information as well. So let's look at how stress strain diagram of ductile material look like. In the region A to B, we have a straight line. What does it mean? It means that stress is directly proportional to strain. That means sigma is equal to E into E. And what is E? It is elastic modulus or Young's modulus, which is a ratio of stress to the strain in region A to B, right? We also know the unit of stress is Newton per mm square. Strain doesn't have any unit. That's why the unit of Young's modulus is Newton per mm square. Now, as soon as we cross region AB, now region AB is also known as proportional limit because stress is directly proportional to strain, right? Once we cross region AB and we go into the region BC, which is an elastic limit, the material behave in an elastic way. What does it mean? It means that whenever you remove the stress, whenever you remove the load, material will regain its original shape and size. But you observe here, it is not a straight line relationship, it has a curve relationship. That means stress is not directly proportional to strain anymore in elastic limit. So what happens when you cross limit C? In the region C to D, we enter into plastic deformation region. That means now your material is not going to regain its original size and shape, even though you remove the load. Now interestingly, point D to E is a very strange behavior, very different behavior which is shown only in ductile materials, right? So this is also called as yielding. Now what is yielding? You may see here that even though your stress is decreasing, your strain is still increasing, right? This is contrary to what happened here. Here you see the stress is increasing and then strain is increasing. But here we see stress is decreasing and still your strain is increasing. This phenomenon is called as yielding, which happens in ductile material. So you will find this yielding only in stress strain curves of ductile material, right? Now point D is called as upper yield point, point E is called lower yield point. After lower yield point, material starts fighting again. That means again in the region of E to F, as soon as you increase the stress, strain also increase, but as soon as you decrease the stress, strain also decrease. So they move in one direction. In region D to E, they were moving in opposite direction. So stress was decreasing, but still strain was increasing. That's why this zone is called yield zone. Now from the figure, you can very well understand stress term. From the stress strain curve, you will very well understand that F is the topmost point of the stress. So if you see here, if you draw the corresponding stress, F is the yield point. F is called yield point, and the corresponding stress is the maximum amount of stress a material can withstand, a ductile material can withstand. This is also called as yield stress. The reason why it's very important to understand, because whenever we talk about yield stress, we have to understand that yield stress is the maximum amount of stress on the ductile material. And how to remember this? Because yielding happens only in a ductile material, so it's very easy to remember, right? So yield stress is the maximum stress on ductile material, and as soon as our material crosses yield stress, it can fail anytime at the breaking point G. So this is how a stress strain curve of ductile material look like. Stress strain curve of brittle material looks a little bit different. And why is it important to understand that? Because purpose is we want to understand what is the maximum amount of stress. In ductile material, it was yield stress. So let's understand what happens in brittle material, because brittle material is not going to show a yielding, right? So this is how brittle material looks like, its stress strain curve looks like. We see there is no straight line, right? But still we can approximately say that stress is directly proportional to strain, and as soon as your stress reaches a P, which is the maximum amount of stress, which is also known as ultimate stress. So whenever we talk about ultimate stress, we talk about a maximum stress. So in the brittle materials, ultimate stress is the maximum amount of stress. This is the threshold. So once we cross the ultimate stress, material can fail anytime. Biggest problem with the brittle material is it doesn't give any warning. Like in ductile material, it will show a lot of deformation. We can see a lot of warnings, cracks will generate on surface. But here in brittle material, crack will generate somewhere inside and we won't even realize unless until it breaks, right? So that's why you have to be very careful when you are designing the material or when you are designing your part with the brittle material. So now that we understand that yield stress is the maximum amount of stress in ductile materials and ultimate stress is the maximum amount of stress on brittle material. So if you understand this, it's very easy to understand factor of safety. So we know the formula of factor of safety, right? It is the ratio of maximum stress to the working stress, right? We also saw in non-technical example, like it was maximum cash divided by working cash, right? Here it is like maximum stress divided by working stress. Very simple to understand. And we also have studied that factor of safety has to be always more than 1. What does it mean? It means that your working stress should or must be always below the maximum stress. Then only your part will sustain. And let's replace this maximum stress for the ductile material, right? We saw in ductile material that maximum stress is equal to yield stress. We already saw that on stress strain curve, right? So if we replace that, we'll get yield stress divided by working stress, and that is our formula for factor of safety in ductile material. And this was our stress strain curve, right? So here graphically you can see that this is my maximum stress and this is my working stress. My working stress is always below my maximum stress. So let's see with the example. In this example, we have given yield stress, and the moment we heard about yield stress, it is ductile material. So we already know that, right? Factor of safety is 2 and working stress will be calculating as 400 divided by 2, right? So we'll get 200. So if we put it in graphical presentation, your maximum stress was 400 Newton per mm square and your working stress you get was 200 Newton per mm square when our factor of safety was 2, right? So factor of safety literally divides your working stress and maximum stress. Now let's see the same example with brittle material. We know that in brittle material that maximum stress in brittle material is what? Ultimate stress. We already know that. So instead of yield stress, now we have to take ultimate stress. And if you see in the stress strain diagram, we are taking ultimate stress and our working stress somewhere here. Now already we know the brittle material show a very dangerous behavior, like they fail suddenly. That's why generally we consider higher factor of safety for brittle material. So in this example you can see I have taken 3 factor of safety. So 450 Newton per mm square was my ultimate stress. The moment I talked about ultimate stress, I talked about brittle material, right? And I took factor of safety as 3, so I got my working stress as 150 Newton. And graphically if I represent that, 450 Newton per mm square is my ultimate stress and 150 Newton per mm square is my working stress. So it's very easy to calculate factor of safety. Now that we understand the significance, we understand that how to look for working stress and where to look for maximum stress in ductile and brittle material. Let's understand the factors which are very important to consider when we choose a factor of safety value. The first factor is a risk to user's life. Means what happens if your part fails? If your part fails and it causes injury or death situation, life-threatening situations to user's life, then definitely you have to take higher factor of safety, right? You want to make sure that your working stress is lower, much below your maximum stress, or otherwise you can reduce your factor of safety. The second factor is life of the part. Some parts like machines or automobile parts or aeroplane parts, they have larger life, 10 plus years of life. Some parts like toys and all, they can sustain for 6 months to 1 year. So they have lower factor of safety. So the lower the life, lower the factor of safety. Higher the life you are expecting, you have to choose higher factor of safety. The third factor is the type of material. We already saw that in ductile material and brittle material are showing very different behaviors. You have to be very careful while choosing brittle materials. That's why when I choose a design for brittle material, I will definitely take higher factor of safety. Fourth factor is type of loading. Now, is your load constant load, or is it varying load, or it is impact load? Definitely if your load is constant load, you can take little or minimum factor of safety. If your load is impact load, bearing load, then you have to go for higher factor of safety. So definitely type of loading will also decide what kind of factor of safety you are going to choose. The fifth factor is bill of material cost. Now we already know that factor of safety doesn't come freely, right? The moment we try to optimize the working stress, that means we have to play with the dimensions, right? We already saw that. And we have to play with the dimensions means what? We have to maybe increase thickness, we have to add ribs, we have to add radiuses, bigger radiuses to take care of stress concentration. So a lot of things will come into the picture, right? That will definitely increase your material cost. Also, if you have to increase the maximum stress, that means what? You have to choose the material with higher grades, right? Which has maximum strength, right? So that will also cost you higher. So you have to consider these factors into your design. If you are designing a nano in the cost of WagonR, nobody will buy that. So you have to consider, you cannot just blindly select factor of safety, you have to also think about the cost. The sixth factor is cost of failure. Means cost of failure doesn't only mean life-threatening situations. Sometimes it might be the inspection cost, replacement cost, warranty cost. If anybody sues you, what are the costs for that? A lot of things you have to consider, right? So if cost of failure is very high, then definitely you want to consider higher factor of safety. If cost of failure is very low, minimum, then definitely you will consider lower factor of safety. And the last but not least, accuracy of your prediction. If you are designing something totally new, first time, and you don't have any data, you don't have enough data, you don't have enough understanding, definitely there is a chance that your assumptions will go wrong when you are calculating working stress, right? So you have to take higher factor of safety, obviously. But definitely we are working, most of the times we are working in the industry which is like for ages it is there. If you are designing a sitting system, they are designing sitting systems since long. You are designing instrument panels, suspension systems, right? Engines, they are there since long. So we understand these systems in very details, and that's why the chances or probability of your assumptions going wrong is minimum, and that's why you have to be reasonable in terms of taking your or selecting your factor of safety. So if the accuracy of prediction is high, lower factor of safety. If accuracy of prediction is low, higher factor of safety. It's very easy to understand. Now here are some values of factor of safety. Even though those could be starting point, there is no standard over it. There are guidelines over it, and guidelines means they could change, right, as per industry. So these are some of the values which generally are considered into design industry. One question I want to ask you. See, if you see here spacecraft, the factor of safety should be higher, right? Because it is a risk to the user's life. What happens if parts fail, right? It is the risk to the user life, and as per our guidelines, factor of safety should be higher. But you see here, factor of safety is very minimum, 1.5 to 3. It's like compared to other industry, it is minimum. So my question to you is, why it is minimum? And not only that, how they make sure that still by taking lesser factor of safety, still the risk to the user's life is minimum. So if you know the answer, you write in the comment box. I'm not going to give the answer. I know the answer, but I'm not going to give the answer. I want to see your understanding of this topic as well. So you give me answer. The question is very simple. I will ask again. Okay, why spacecraft designs take minimum factor of safety like 1.5 to 3, and how they tackle the situation of risk to the user's life even with the minimum factor of safety. So you need to answer this question in the comment section, and I will give the answer. Don't worry, I will give the answer in comment section after 2-3 days. First you have to answer, right? And if your answer is correct, I will like that comment. I will say that your answer is correct. So this is all about factor of safety. I'm sure that you have understood this concept in details now, and you'll be more confident in choosing factor of safety. Also, you might have understood one thing, that factor of safety is not very constant throughout design. It improves, it evolves. As we understand more, we can optimize, or we can reduce this buffer, we can reduce the factor of safety, we can reduce the difference between working stress and maximum stress. So I'm sure that this video was helpful for you and you'll never forget this concept of factor of safety in your life, and you'll be more confident when somebody asks you about this concept, and not only that, you'll be more confident in using this concept. And my friends, if you're not done yet, please consider subscribing to my YouTube channel. You can approach to me with your questions on kevinkutto@gmail.com. So thank you very much for watching this video.